In this video, we are going to go through some theorems. Theorem 1.3, let P be a prime number. So let's say we are assuming P as a prime number. P value is 3. Okay, this is our assumption. If P divides A square, then P divides A, where A is a positive integer. So let's say that A, which is a positive integer, we are taking its value as 6. Now definitely if A is 6, A square will be equals to 6 square. 6 into 6, which is 36. So according to this theorem, what we understood is that if 3 divides A square, which is 36, then 3 will divide 6 also. So the same way you can understand that if 2 divides 36, then 2 will divide 6 also. So this theorem is nothing but the application of fundamental theorem of arithmetic. In this, what are we understanding is that if you have a prime number, let's say that is 3, and if it is dividing the square of a number 36, if you are dividing 36 with 3, you will have no remainder, right? So if 3 divides 36, then 3 will divide the square root of 36 also, which is 6. So 3 will divide 6 also. Same happens in this example also. You can observe if 2 divides 36, then you can say 2 divides 6 also. Now using this, we are going to prove the next theorem, which is Theorem 1.4. It says that we have to prove here that root 2 is irrational. Now, in order to prove this theorem, we are going to use method of contradiction. Method of contradiction. What is the meaning of this method? That it implies that we are going to assume something first of all wrong. Okay? And based on that wrong assumption, you will get the result also wrong. So we will conclude that our result is wrong because our assumption was incorrect. So this is the way we have to prove Theorem 1.4. Here, let's assume first of all root 2 be a rational number. Be a rational number. So we have to prove over here that root 2 is irrational, right? We are starting with a wrong assumption that let root 2 be a rational number. So it means that if root 2 is a rational number, you can write down root 2 in the form of P upon Q, right? Where Q is not equal to 0. Along with that, P and Q, they are coprimes. Coprimes. Now what is the meaning of coprimes? It basically means that the HCF, the highest common factor of P and Q, will be equal to 1. You can write it down like that is HCF of P and Q is equals to 1. So if root 2 is a rational number and it can be written in the form of P by Q, where Q is not equals to 0, therefore here P and Q are coprimes, and the HCF of P and Q will be equals to 1. So, if we will try to cross multiply this Q, we will multiply it with root 2. We are going to get root 2Q equals to P. Now, in the next step, we will square both the sides. So, on squaring, both sides, we'll get root 2Q whole square, which would be equals to 2Q square, and square of P will give us P square. So according to this, what can be conveyed? That we can write it down in the form of Q square is equals to P square upon 2. which means that here 2 divides p square. Now according to our previous theorem, if 2 divides p square, we can conclude that it will imply 2 divides p also, right? If 2 divides p square, then according to the previous theorem, Theorem 1.3, we can write down 2 divides p also. Now, here we will write down, let p by 2 equals to c. Let p by 2 equals to c. So, according to this, p will be equals to twice of c, right? P will be equals to twice of c. Now, this value of p, we are going to substitute it in this equation. Let's number this equation as equation number 1. So, we will write down, put value of p equals to 2c in equation 1. We can write it down, root 2q equals to, in place of p, we will write down 2c. Now again, after this step, we are going to square both the sides. So on squaring both the sides, we will get 2q square equals to 4c square. And hence, we can simplify it further, which can be written as q square equals to 4c square upon 2, which can be written as 2c square. So we got q square equals to 2c square. Q square equals to 2c square. Therefore, we can write it down in the form of q square by 2 is equals to c square. Now with this, what did we understand? That definitely here 2 divides q square. And if 2 is dividing q square, then it will imply that 2 divides u also. So here we are going to write down q by 2 equals to, let's say, some number d. Let q by 2 equals to d, which implies it can be written as q equals to twice of d. Now here in the previous case, we assumed p equals to 2c and we got q equals to 2d, which means you can observe in both of them 2 is a common factor, right? P and q, both of them are having 2 as a common factor. But according to the definition of rational numbers, what did we wrote it over there? That if root 2 is equals to p by q, then p and q should be co-primes, right? They should not have any other common factor apart from 1. But here, as a result, we got that p and q are having 2 as a common factor, which implies that we can write down p and q cannot have two as a common factor because according to our assumption, p and q are co-primes, right? Which means HCF of p and q should be equals to 1. It should not be equals to any other number. Now here there is a contradiction, right? We assumed something and as a result we got something else. We got p and q have 2 as a common factor, but we assumed in the initial part, we assumed that p and q are co-primes. Now this contradiction has arisen because of our wrong assumption. because initially we assumed wrong thing. Therefore, we will write down this contradiction has arisen because of our wrong assumption. That root 2 is rational number. So, if this statement root 2 is rational number, if this assumption is wrong, then what is the correct statement? Definitely it will imply that root 2 is irrational number. Right? If root 2 is not a rational number, then what is the other way around? Definitely root 2 is a rational number. So this is called as method of contradiction. We assume something incorrect, and based on that, the result we are going to get as wrong, right? So we conclude that the contradiction has arisen because our initial assumption was incorrect, and hence we conclude that definitely root 2 is a rational number over here.